Hi Geometry, welcome back. Today we are going to be going over 4.2a and we're going to be talking about isosceles triangles, their side lengths, angle measures, and how we can relate them. But before we get started, I want to see how much you remember from yesterday. So go ahead and try this warm-up problem. So see how do you remember if you tell if two figures are congruent, and then find rigid motions that map triangle ABC to triangle FED. So go ahead, pause the video, give it a whirl, and then press play when you're ready. All right, so here is the answers for the warm-up. So you'll see that the first thing we need to do is we need to take triangle ABC and we need to move it down 6. So we see that C and D match up. We see that B and E match up and A and F match up, which is what we see up here. And then once we do that, we need to switch the orientation on ABC, and we see that they are both 1 away from the y-axis. So that's the line right down the middle of them, the midpoint between their corresponding points. So we reflect over that y-axis, and so we have a composition of rigid motions. So we know two figures are congruent if there are rigid motions that map one to the other. We have a composition of rigid motions mapping one to the other, so these figures are congruent. So getting into the content of today, talking about isosceles triangles. So you'll remember that an isosceles triangle means it has two congruent sides. So in this case, I'm going to say that AB and BC are my congruent sides. So a little bit of vocab here. We talk about base angles. So base angles in this case is going to be angle A and angle C. And then we have our vertex angle, which is angle B. So we know that AB and BC are congruent. So that's kind of our known. AB and BC are congruent. So let's say that I draw a line of reflection right down the middle of the vertex angle. So I'm going to call this line L. So let's say that we reflect this triangle, this kind of left side triangle, over that line of reflection. We know that AB will lay right on top of BC because they are congruent. So if we take the reflection over line L, that angle of BAC, or angle A, is also going to be congruent to angle BCA. So that means, or that's not congruent, that's equal to. The reflection is equal to that angle. So since that reflection lines up, that means that angle BAC is congruent to angle BCA. So when we have isosceles triangles, the base angles are congruent. So this leads us into theorem 4.1 and its converse. So theorem 4.1 is the isosceles triangle theorem. So that's on the left side in that left-hand little square. And that says if two sides of a triangle are congruent, if we have an isosceles triangle, then the angles opposite those sides are congruent. So let's say we have our triangle ABC right here. AB and BC are the congruent sides. So that's our hypothesis. So if that statement is true, then the angles opposite them, or our base angles, also have to be congruent. So if those two sides are congruent, the angles opposite them are congruent as well. And then we also have the converse of that statement. So you'll remember back in chapter 1, we're just flipping the hypothesis and the conclusion. So if two angles of a triangle are congruent, so if I tell you that angle BAC is congruent to BCA, then the sides opposite those angles are congruent. So that would tell us that AB is congruent to BC. So let's put those into practice. So this first slide here is going to be going through 4.1, so the isosceles triangle theorem. So if we look at this triangle right here, we want to find the value of x. Well, the first thing you'll notice is that we've got a little tick mark here and a tick mark here. So that means this side and this side are congruent. So by the isosceles triangle theorem, that means that this angle has to be congruent to this angle. So that tells us that this angle's measure is 28 degrees as well. Using the interior triangle angle theorem, we know that all three of these angles have to add up to 180. So if we go 28 plus 28 plus 5x plus 9 equals 180. Doing a little bit of math on this, we get 65 plus 5x equals 180. Subtract the 65 from both sides. 5x equals 115. So x is equal to 23. All right, I want you to pause the video. I want you to give the second one a try on your own and then press play when you're ready. All right, hopefully starting off this problem, the first thing that you noticed is that we again have two congruent sides. So that means we can use our isosceles triangle theorem. So since these sides are congruent, that means the angles opposite them have the same measure. So we can say negative 4x plus 9 is equal to 8x minus 3. So let's add 4x to both sides, and let's add 3 to both sides. So we end up with 12x is equal to 12, which just gives us x is equal to 1. So that's how we put the theorem in practice. What about the converse? So we now want to find the lengths of all three sides of each triangle. So this first triangle right here, we are shown that angle P is congruent to angle Q using those angle markers. By the converse of the isosceles triangle theorem, the sides opposite those angles have the same measure. So we can say x plus 20 is equal to 8x over 3. So everybody knows that the worst part of math is fractions. So let's get rid of that fraction on the right-hand side. Let's multiply both sides by 3, because if we do that, then this cancels with that. So the 3's cancel, we no longer have a fraction. We have to distribute this 3 on the left-hand side. So we have 3x plus 60 is equal to 8x. Subtracting 3x from both sides, we have 60 is equal to 5x, and then dividing by 5, x is equal to 12. So now we know what x is equal to, but we are looking for the length of the sides. So we want to take that, plug it right back in up here. So 12 plus 20 is going to give me 32 for PR. And yeah, we could plug in 12 into here, or we could use our isosceles triangle theorem, or just our knowledge of isosceles triangles rather, and say, all right, well, this has to be equal to this. So this is 32. Next, we have to find the length of this side here too. So we do have to plug in 12, so 6 times 12 minus 12, and that's going to give me 60. So same thing as I did on the last slide, I want you to pause the video, I want you to give this second one a try, and then when you're done, press play. So, same thing that we started with on the other problem. These angles are congruent, so that means that those sides have to have the same measure. So 8x minus 1 is equal to 4x plus 5. Subtract 4x from both sides, add 1 to both sides. We get 4x is equal to 6, or x is equal to 1.5. So let's plug that in up here. 4 times 1.5 plus 5 is going to give me 11. And then again, we can just use our knowledge of isosceles triangles that these sides are the same. This is also equal to 11. And then we have 2 times 1.5 plus 11, which is going to give me 14. So before we end today, I have one more theorem for you. And this is theorem 4.2. So we're going to read through this. There's a lot of words in here, a lot of really math, geometry type words, and then we're going to break it down. So our theorem states that if a line or line segment bisects the vertex angle of an isosceles triangle, then it is also the perpendicular bisector of the opposite side. Whoa, that was a lot. So let's put it into pictures because visuals are going to make it a lot easier. So we say a line or line segment, so I've drawn that in here in this dashed line, bisects. So remember, bisects means cuts in half, exactly in half. The vertex angle, so that's going to be angle B up here, of an isosceles triangle. So what we know is that AB and BC are congruent, and then we know that this line here bisects B, so the measure of ABD is equal to the measure of CBD. So that's our hypothesis. So if that all is true, then our line, our dashed line, is also the perpendicular bisector of the opposite side. So if all of this holds, that means that this dashed line is perpendicular to the base. So that's why we've got this nice little box right here that tells us that this is a right angle, because that's what perpendicular means. And then bisector, again, means it cuts it in half. So that means AD is congruent to DC. So let's put this into practice. We've got one last problem for today. So we want to find the measure of angle RSQ, and then we want to find the length of the side PR. So let's start with the length of the side PR. So we know right here we have an isosceles triangle because this side is congruent to this side right here. And then we are shown that this angle is congruent to this angle, which I drew over. So that means that this line bisects our vertex angle, and we have two congruent sides here, so we can use theorem 4.2. That means that this is perpendicular and that this side is congruent to this side. So that means that PQ has a length of 4. So to find PR, we just have to do 4 plus 4, and that's going to be equal to 8. Now, to find the measure of RSQ, we're going to use our internal triangle angle theorem, all right? So using our knowledge of isosceles triangles, remember that we have this side and this side are congruent, so these angles have to have the same measure. So this angle's measure is 31 degrees. We know this one is 90 because it's a perpendicular bisector. And then let's call this x, just so we can put it into an equation. So if we add up these three angles, we have 90 plus 31 plus x has to be equal to 180 degrees. So this gives me 121 plus x is equal to 180, or x is equal to 59. So the measure of this angle is 59 degrees. That's all I've got for you on 4.2a, so go ahead, get started with that Pearson homework, and I'll see you back here tomorrow to talk about equilateral triangles in 4.2b.